Bear with me. And I hope that this is not showing up on your screen the way that it does on mine. Let's get started with z equals cosine x plus cosine y plus sine x. So I'm going to start by holding x equal to a constant. When x is a constant, then sine of x is a constant. It's some other constant. And I get z equals cosine y plus a constant. So I should get a cosine curve in the y direction when I slice along the x-axis. Now, I don't know, because these aren't labeled, which of these is x and which is y, but I also can see that the same is true that if I held y constant, I would get z equals a constant plus sine of x, so I should get a sine curve in that direction. So I know I'm definitely looking for, whichever direction it turns out to be, the same kind of a sine curve in one and a cosine curve in the other, so wiggles in both directions, I believe is the technical term. So that's going to let me rule out a lot of these. This is not sufficiently wiggly, nor is this one. This is a possibility, so I'm going to leave that not sufficiently wiggly. A little wiggly, but not really in the way that cosine and sine are wiggly, so say goodbye to that one. This one gets to stay, very wiggly. This one also gets to stay because I can kind of trace. So sort of wiggly, possibly wiggly. This one is not wiggly. So I've narrowed it down to 3. And if I set z equal to a constant, then I'm going to get a constant is equal to cosine y plus sine x. And if I tried to solve that, I would end up getting something with y is arc cosine of a constant minus sine x. And whatever that is, it's not the equation of a circle. Whereas on this graph, if I set z equal to a constant, I expect to get a circle. So I'm going to rule out that. And it's also definitely not the equation of a straight line, which seems to be what happens if I set z equal to a constant here. So I'm going to rule out this one too and lock in on 3. Another thing I can use as a hint is that when I'm looking at this, if I switch y with negative y, I should get symmetry, because cosine of negative y is the same as cosine of y. If I switch x with negative x, then I should not get symmetry, I should get reflection. So I'm kind of seeing that happen here, that in one of these directions, assuming the axes are in the middle, which I should assume unless told otherwise, in one of those directions, I sort of have symmetry, that what happens on this side happens on this side, and the same here. But that's when I look at it in sort of facing this way. On the other hand, if I face this way, I have the opposite symmetry going on, that when one goes up, the other goes down. Same if I look at the symmetry along y equals x, I shouldn't get a perfect symmetry, because when I switch x and y, I get a new function. It's definitely related. Cosine x plus sine y should look kind of similar to cosine y plus sine x, but it shouldn't look identical. And if I'm looking at these two, I think if I go along the line y equals x, which either looks like this or like this, I'm thinking if I fold along either of those, I'm going to get back the exact same thing. Whereas in this one, I shouldn't get back the exact same thing based on my equation. And I don't, that if I flip along here, this one is going up and this one is going down. And same over here and here. So because of the symmetries that should and shouldn't be there, I'm going to feel pretty confident about saying A should be 3. Now, B is its own story, so I'm going to clear what I have so far. B is given by z equals x times y. And so if I set x equal to a constant here, I'll get z is equal to a constant times y, which is the equation of just a straight line. And same if I set y equal to a constant, I'll get z is equal to a constant times x, which again should give me a straight line. So I'm about ready to choose which one I want. There's only one of these where I feel like I'm getting these nice straight lines in both X and in Y. And sure enough, it looks like my slope is increasing or decreasing. It's definitely getting steeper as I move either X or Y, which is also pretty consistent with the fact that as X gets bigger, the slope for Y is bigger, or vice versa. I can see that this line points up more than this one, and then this one then points down. And that's also pretty consistent with if I swap out negative X and negative Y. I'm just going to check for my understanding. I'm going to double test against the end behavior for this one, that if I let X and Y either both go to positive infinity or both go to negative infinity, then Z should be going to positive infinity. But if I let them have opposite signs, if X goes to positive infinity and Y goes to negative infinity, or vice versa, then Z should go to negative infinity. And that also feels pretty consistent with 2 to me, that I'm sort of on opposite quadrants, kitty corner quadrants, I'm going up, and then in the other kitty corner quadrants, I'm going down. So I feel pretty good about saying that B should be 2. Let's look at C. C is given by Z is equal to 1 over 1 plus X squared. Now, if I set X equal to a constant, I'll get Z is equal to a constant, so a straight line. And if I set Y equal to a constant, I'll get Z is equal to 1 over 1 plus X squared, which is a curve that you might remember from previous calc classes, looks vaguely like this. And that kind of matches this one. And in particular, what's cluing me into this one is the fact that I do get the straight lines in the other direction. And I would say this is really the only one where I get straight lines in one direction where it doesn't change as a function of one of the variables. In fact, I can go further, and for this one, I can tell you which axis is X and which is Y, because it doesn't change along the Y axis. It's the same no matter what Y you put in. It only changes as X changes. So I'm feeling very, very confident about saying C should be 1. It's the only one of these graphs that is not really a function of both variables, doesn't change in both X and Y. For D, I have Z is equal to cosine of X plus Y. So again, I'm looking for a cosine curve, which again is narrowing me down to 3, 6, and 7. Now, I can rule out 3 because I already used it, but I'm also looking at the fact that if I have X plus Y, then it doesn't matter if I switch them. If I switch X plus Y, if I switch that and get cosine Y plus X, that's the same thing. So I should have this symmetry going on in X plus Y. And if you remember when I was looking at 3, 3 didn't have it. 3 didn't have quite the exact symmetry we needed, whereas 6 and 7 do. This nice sort of X-shaped symmetry. Now, the other thing I'm going to look at, what if I set Z equal to a constant? Then I will get a constant is equal to cosine X plus Y. And again, if I solved that, I would end up getting Y is equal to arc cosine of a constant, which is just another constant again, minus X. So I should get just lines. I should get Y is X or minus X, whichever, plus a constant. And this one looks like it's giving me lines when I set Z constant. This one looks like it's giving me circles when I set Z constant. So I'm ruling out this one. Sorry, ruling out this one, and I am choosing this one. So D should be 6. Let's look at E, where we have Y squared minus X squared. Now, after doing today's 241 worksheet, I might just know immediately what this is, but let's try anyway. If I set X equal to a constant, then I'll get Z equals Y squared minus X squared. So I should get an upward opening parabola in one direction. If I set y equal to a constant, I'll instead get z equals a constant minus x squared, so the downward opening parabola in the other. And that really seems like it's hinting one of these to me. I'm thinking the only one that really matches that, where I get one parabola one way and another parabola the other way, is graph 5. Doesn't really have any particularly strong special features, although it is symmetric about both the x-axis and the y-axis. That is, if I plug in negative x instead of x, I get the same shape. And if I plug in negative y instead of y, I get the same shape. So the only other one that I might consider is this one, because it's got a similar kind of curve going on, sort of down there and up there, but that's not happening parallel to the axes. That's not happening when I freeze x or y. That seems to be happening when I freeze some relationship between x and y. Plus, you know, I already used that one. So I'm pretty happy to say that this has to be 5. For f, we have absolute value of x minus y. Absolute value was one of the things that I'm kind of on the lookout for, because I expect it to give me a nice crease. And the only one of these that I see that really strong even crease is this last one. And that makes sense that if it wasn't for this absolute value, if I had z equals x minus y, that would be a plane. That's just the equation of a plane. And when x minus y is greater than 0, then it gives me exactly that plane. Or when x minus y is less than 0, then absolute value of x minus y is the same as y minus x, so that should give me another plane. So the absolute value in this case, because I have x minus y on the inside, is telling me I should have 2 planes, and they're kind of intersecting where x is equal to y. They go along this line where z is 0. The only one of these that looks really remotely plane-like to me, let alone 2 planes, is going to be number 8. So I'm going to say f is 8. Let's clear all drawings. And for g, I have z is equal to log of x squared y squared. Now, log is a big hint to me. Something weird should happen with log, because I'm never allowed to plug in 0 or any negative number. I don't really have to worry about any negative number, because by taking x squared times y squared, if I plug in negative numbers, when I square them and multiply them, they'll become positive. But I am worried about 0. If I plug in either x equals 0 or y equals 0, I expect log to go crazy. I expect to get an asymptote there, really. And there's really only one of these graphs that looks like it has an asymptote of any kind, and that would be number 4. I can sort of see that if I'm along the line y equals 0 or x equals 0, I don't actually have a point on my graph that corresponds to either of those. Pardon my bad axes drawing that it looks like I do, but I'm sort of falling into this gulf where the function shoots downward very quickly off towards negative infinity. So because I have the log, because I know something in my domain isn't quite right, and every other function doesn't seem to have a problem defining the function when x and y are equal to 0, based on these other graphs, based on the fact that none of them have asymptotes along x equals 0 or y equals 0, I'm really ready to say that g should definitely be 4. And that leaves h, which I could say, okay, process of elimination, there's only one of these graphs left. I'm also going to check my understanding that I know it's sine, so again, I'm looking at a sine curve. I'm looking at one of these 3, either 3, 6, or 7, but also I finally have this x squared plus y squared that I've been on the lookout for, and that means I should get circles in z. Because if I set z equal to a constant, and then I take the arcsine of both sides, I'll get arcsine of a constant, which is to say a constant, equals x squared plus y squared. So I should get circles when I slice in z, and I finally got them. I can finally use number 7. So very quickly, let me say again, I said that a was 3, that b was 2, that c was 1, that D was 6, that E was 5, that F was 8, that G was 4, and that H was 7. So I'm going to see if I can erase just the parts that I just put. Just this and this. Nope, I am actually going to have to clear all my drawings because now I want to start looking at the contours.